Thank you, Dr. Vogel, for the introduction and the possibility to present at this stage. The talk will be on thin film encapsulation to enable flexible and transparent moisture barriers. And if there will be some time at the end of a talk, we can also make some flash survey. And for that, I will ask you to prepare an internet browser at this page. But we'll see. If we have time, we do it. I think it will be also fun. So let me start with some words of introduction about Meyer Netherlands. Well, we are equipment manufacturer. We have two areas of focus. One is functional inkjet printing, and the other is coating, thin film coating. And we use PCVD and ALD as base technology in our company. We are in Eindhoven, in the Netherlands. We are part of a worldwide Meyer group, and this is nice when we have to assist our customer spread all over. And we can also benefit from some support from other local teams. We are 90 people in Eindhoven, and we have quite a bit of history on equipment manufacturing. We've been founded more than 30 years ago now. I would like to bring the attention to this chart, because in here you can see how we connect our expertise on thin films and inkjet and clustering of processes to the application that we wanted to target. We have in our roadmap the OLEDs and displays, photovoltaic and battery as part of energy, and printed electronics and semiconductor. So what we see in here is that we actually are able to use the three expertise in all of this application, and that's why we focus on those. And this is the family portrait. Well, let's be a little bit more serious on that. We have here some equipment that are from the inkjet department. With these we deliver functionality for the printing. We have also for the coating equipment that can provide PCVD coating, and we have those at different scales. Actually, we start from an engineering scale, a laboratory scale, which is very versatile, very many configuration can be made, and various settings can be imposed with a tool. We go to a pilot production, which is still flexible and will still enable a lot of process optimization and fine-tuning. But we also know that once this phase are finished, then it's just about production. So you take what you know from a pilot and from engineering, and you want to have it running over and over and over and over at a very high reliable rate. And for this reason, we also make a different kind of machine that will basically take care of this reliability. What happens also is that the size scales up when you go to this kind of application. We have seen our equipment, we've described the company, but now let's be back on the application, on the topic of the talk, which is DFE barriers. Here at the center of the circle. So what the customer wants is a barrier, and a barrier most of the time, because of the application areas, which are OLEDs, batteries, or PV, will be a moisture barrier. And a moisture barrier is characterized by what is called the water vapor transmission rate. And when we give a value to it, it will be given in grams per square meter per day. One number which is very much written in the literature is this 1e-6. So if you reach this level, you can talk about having a thin film encapsulation barrier of any worth. Now, what do we do to achieve that? Well, we said we have some equipment for it, but is it enough? Well, not really, because what you still need is to run a process on this equipment, and equipment plus process will still need some, let's say, consumables, so some materials. Why is it a circle of influence? Because what we have tried in the past years is to get all the pieces of a picture. So we provide equipment. We are in contact with internationally renowned research center focusing on TFE barriers, and we are in contact also with material suppliers in order to make a test of this application of these barriers, and therefore be able to deliver to a customer a working solution. So we talk about barriers. This WVTR, we said about the 1E-6. Well, let's say that also 1E-4 can be good for some application. So the typical can be within this range. Our company can provide a sheet-to-sheet solution. So maybe the willingness to make a single barrier sheet for later lamination, or to directly encapsulate the active device, which is pretty common, or will become more and more common for OLEDs. And for these, to do that, we are using inkjet printing of organic and PECVD coating of silicon nitride. So in the end, we are going to do a device coating which looks very similar to this. So there is an active material that needs protection, and then a dyed of silicon nitride and organic coating, and silicon nitride on top coat to protect from the outside. For roll to roll, we can also offer roll to roll solution, and there the target will be to realize a roll of foil barriers for the lamination. And direct encapsulation is a little bit more challenging because you have to have rolls of devices. So still possible, but we see this with a longer breath in time. And for that, you might want to couple the technology. Let's say we demonstrated the coupling of slot die of an organic or inkjet printing of an organic together with atomic layer deposition of aluminum oxide. So let's start from sheet to sheet. And why do we do that? Well, as we said, that we have, I would like to make this sketch a little bit larger. So we see again the active material. And in this case, I brought in a cathode, meaning that most of the time, like for OLEDs, which is a typical application, we talk about a cathode and the degradation of a cathode, which happens in spots. So why does it happen, and why do we want to do such stacking? Well, the reason is because of defect density. Defect density of inorganic coating, which are ideally perfect barriers. If you don't have any defect, you can have a single inorganic coating overall and you will be fine. But reality is that there is a density of defects, and it can be very low. And in fact, you can influence it by using automation and using clean environments, but it's impossible to bring it to zero and be certain of it. So what we do, or has been done for many decades, is to decouple it by using an organic coating. So we use what is called the tortuous path. So water comes from a pinhole, whatever it is. It will have to diffuse through the organic. So diffusing, and then it will eventually have enough partial pressure at the location of a second pinhole to penetrate again. Pinholes anyway are filters. It requires a certain difference in partial pressure of water to have water coming through, and the flow is every time you pass through pinholes, the water flow is very, very much decreased. So we have this penetration, but what you can also realize is that there is a lag time before the water can actually get there and start a defect. So you not only get a low WVTR, but you get some sort of dynamic one. So it will be zero until this whole story will go through. And even even when wet is done, the defect will grow very slowly because of this, because of the principle we set. Now, we have seen where we want to be, and the reality is that we deliver equipment. So we actually deliver the golden knobs. So what you can see here, which in the end is basically the how. So how do you do these things? You're gonna set some alignment requirements, and let's see this for the example of the organics, for inkjet printing, for example. So you have a set of equipment settings, so alignment, movement precision, ink, which ink you're gonna use, which jetting setting, which print setting, curing, maintenance. All of these, when set it properly, will influence the layer properties. So what you're gonna do, it will influence how you position the layer, the thickness of a layer, the edge control of a layer, and shoulders of a layer. So when you have this control, when you have this layer properties in control, you also know that these properties will end up in the requirements. So basically, this is how, this is what you do, and this is why you do it. So eventually the customer comes with a certain why. He has some ideas in mind, he knows why he wants it, and therefore we can start our machine design going through this table. And going through this table in this way means that we have experience of going this way. And in the end, this is always process fine-tuning. So let's have a look about positioning. So what can be achieved, for example, in our machine? And for printing, we can, by coupling the movement precision, the alignment, the jetting, and the maintenance, all of this affect the print positioning, and therefore we can achieve positioning of plus minus 50 micrometer at 3 sigma. Here's an example of placing a certain edge at a certain distance on a square position, and we demonstrate this on several plates in several locations, making this measurement, and then we demonstrate this plus minus 50 micron. If you know that you can position at these levels, you know also that you don't need to take much more space. The design of your encapsulation will actually depend on this number. So the smaller this number is, the less space you can take on your substrate. Another thing which is important for organics is their thickness. And again, you can influence the thickness by setting the right print setting, choosing the ink and the surface properties, and therefore in the end you will come out with some certain height profile. What we have been testing in our laboratories is with the same ink and same surface, we were able to do a wide range of thickness. Of course, we had to change print settings, and the good thing was about the uniformity of this level, of this layer. From a certain moment on, we can ensure that the layer will be flat with a standard deviation which is approximately 1% of the average value. We can go again through this table for the case of inorganics, and particularly for plasma-enhanced chemical vapor deposition of silicon nitride. Again, we have some knobs, which are pressure, power, gas settings, and temperature and maintenance. And then we go through this, we can influence layer properties of thickness, refractive index, conformality, and composition, and this will turn out to fit the requirements from the customer. And again, we will sit at the table with the customer, discuss the requirements, and therefore find out which is the machine which is needed. And in the end, we will also go through a process fine-tuning to see if it all works out. Now, looking at thickness, for example, we give also some freedom, meaning that it is possible to change the pressure and the gas settings to influence the deposition rate. Well, the deposition rate together with the timing will give you the thickness, but it will also give you the throughput. So that's why I bring here the deposition rate instead of the thickness. About thickness, we can of importance is its uniformity. So we have example of uniformity of plus minus 5%. And another important thing about inorganics is the conformality. It's very challenging to coat surfaces which present deep trenches, so micrometers trenches or more, or negative surface angles, like in these two cases where you see an explicitly performed trench, or you see here a negative angle, so a feature that needed to be coated. What you see here in white is silicon nitride. And you see that it's possible to have this coating everywhere, but the thickness will not be exactly the same everywhere. So we can coat, but it cannot coat uniformly everywhere. Now the second question that arises is immediately, okay, we decided to coat, for example, 500, 1000, 300, whatever thickness. Will then the limited amount of thickness that is coated on these special surfaces be enough? And for that reason, we had a look at the intrinsic WTR at thinner layers. So we went down to 300, 150, and 75 nanometer, and we could find consistently that these layers were able to match the expectation. Now, this scale is logarithmic, and what you see is that basically there's no difference. They all perform in the same way. We're all in the -6 region. Now, when we talk about inorganics, for roll-to-roll application, we have this spatial ALD atomic layer deposition configuration. So the principle of ALD is to use two precursors and expose the surface to these two precursors at different moments. Now, it can be done in time, meaning you have a chamber, a substrate, you fill the chamber with precursor 1, you purge the chamber, you fill it with precursor 2, and by repeating this cycle, you will start growing a layer. Now, a possibility to extend this is to use, instead of time, use space. So you could have, like in the example above, a moving substrate and a fixed chambers where you have only precursor 1 or only precursor 2, but the position of the web will change. And you can even go even further. You can put all of these chambers in a roll, in a drum, and therefore you can, by moving the drum or moving the web or moving both, you can achieve this spatial ALD. Now the growth rates are above 1 nanometer per second. It can be done at atmospheric pressure. There's no contact to the web. There's a wealth of materials in the R&D stage that can be deposited with this technique. Most established is aluminum oxide, but many others are on the way, and the literature gives many examples. And there are even some which are already demonstrated at the roll-to-roll level, and ALD and aluminum oxide is one of them. So what do we look at when we have aluminum oxide? We look at the growth per cycle. Why do we look here? Because, as we said, this is a certain reaction that needs to take place, and it takes place during a cycle. So what you can expect is that what you do in a cycle is always the same. It's just what we are playing with is how quickly can we switch between cycles. Now, this growth per cycle is actually a signature of the machine. We can therefore verify if the machine works properly, if we achieve a certain theoretical saturation curve. And we can influence this by changing the TMA pickup flow or the water dose. And what we see is that we could match in our machine this theoretical level, which means we have an ALD process in place. So we went to a very classical time-based ALD, we move it to all spatial, and we find it again. So all good. Now, let's see what are the advantages of having something like that. This will ensure almost intrinsically uniformity. It depends on gas showering and so on, but these are all mechanical things that we can handle, we have experience on. So the uniformity, it's some sort of present you get from the construction. And what we demonstrated is that it was possible, like in this case, to make 72 nanometer of ALD with 96 cycles per minute, which if you count to a layer thickness of 20 nanometer, which would be enough for a barrier, you can coat 42 square meter per hour, which is a quite good achievement. Now, we deposit this. We talked about the 20 nanometer. Does it work? Well, if we deposit 20 nanometer on 125 micron of PET foil, you will get WVTR in the region of 10 minus 5 at 2050. So the barrier properties are validated. This leads me then to the last slide on the topic. We are offering mature technologies. We illustrated how to get from equipment settings to desired functionality. The tools give a user easy control over the process window to match the desired requirements. And clustering of equipments enable the stacking, which is vital for technical application. Now, do you want to know more? Are you interested? Then come and visit us at the Maya Burger booth. I've brought from the Netherlands a wealth of brochures, and I think you can have a look at those. Thank you very much for your attention, and we have still 3 minutes for questions. And if we can deal with a question, then there is still the survey. In the meantime, maybe you can pair on this. Thank you very much.